okay? Differential equation, right? A couple of more of these differential equations. So we'll have a slope field here, okay? Oh, this is the question. So this differential equation, x over y, right? dy dx equals negative x over y. We'll have a slope field with negative slopes in all quadrants, okay? We'll have a slope field with positive slopes in all quadrants. We'll produce a slope field with rows of parallel tangents. Now, the thing is this actually will not, this is not true, the first one. It will not have negative slopes in all quadrants. The only time it can have negative slopes in all quadrants is if the slope itself turns out to be always negative. Now, in this case, we've got a negative x over y, right? So a negative x over y. And sometimes this is going to be negative. Sometimes it's going to be positive. But not all the time. So let's, for example, take a few questions and see. So for example, if I have this quadrant here where the x is positive and the y is also positive, then this is going to produce negative slope fields, right? Negative slopes like that. And over here where the x is negative, I guess I could write less than 0. And where y is less than 0, I'm also going to get negative slope fields here, right? So it's always going to have negative. But over here, it's actually going to have positive slope fields and positive slope fields here as well, okay? And so in the end, neither of these first two are correct, okay? And here it says, will it produce a slope field with rows of parallel tangents, okay? So rows of parallel tangents look, let me erase this. Rows of parallel tangents look like this, okay? So it's like that, meaning it doesn't matter what the x value is, this will always have the same slope for this y coordinate. And slope fields that look like that actually don't have an x in them, okay? They don't have any x's in their differential equation, okay? In their first order differential equation, all right? So, so there it is. So basically it would be things like this, you know, which basically means that at this y value, the slope is always this, meaning the x value, this x value right here, for example, and this x value right here, it doesn't matter. So as the x value changes, the slope stays the same. What things look like that? So it would be dy dx equals just like a y, for example, or maybe like a 2y, right? Those are going to have slope fields that have whole rows of parallel tangents. So as it turns out, there's none of the above for this one, okay? None of the above. Here, this is a good question. The slope field below is for which differential equation? They must give us some. Okay, so they give us a few differential equations here. And look at this. It's rows of parallel. See that? It's a row. You see this row right here? It's a parallel slope field. Here's another row with a parallel slope field. I keep saying that wrong. The slope field has parallel slopes in rows. That's what I probably should be saying. And that means I have to choose a differential equation with no x's in it. So that would be this one here, okay? That one there. Over here, it says match the following slope field with the appropriate differential equation. Now this, again, I think these answers are not necessarily correct. Now they might be correct. So here I've got, let's see, y prime equals a negative x. All right, so that means the slope is always equal to the negative x coordinate. All right, so if I look at my x coordinates here, here we go. I think it's, where is it? I believe this one. This one right here is A. Why is that? Well, because what's my x coordinate here? My x coordinate is 1. And what's my slope? -1. And it's -1, -1, and all of these locations. So just like how before, how if we have rows of parallel slopes, there's no x. When there are columns of parallel slopes, there's no y. Okay. And that's what we've got there. Okay. So that's pretty cool. Now, I'm going to move this video because it's just not working. All right. Maybe I'll stop the video. Start again. It's very strange today. Guys, I'm so sorry about that. Whatever. You guys don't need to see me. Now, over here, this one. So that one was A. We decided that one was A. So we'll cross A off. Over here, let's talk about this one. What's my slope? I'm gonna focus on this right here. It looks like when the y coordinate is, I don't know, 1. Is that a 1? When the y coordinate is 1, I've got a slope of 0. So look, if I put a 1 right there, what's 1 minus 1? 0. Bang. So therefore, this guy, I'm just going to go right there. You see that? Focus right on there. So let's, yeah, I think that's pretty good. Same thing here. What do we got? When I've got a y coordinate of, let's see, 1, 2, it looks like it doesn't actually look parallel. It looks sort of parallel. Let's take a look at it. There it is. It's true. When I have a 2 as my y coordinate, so what's 2 minus 2? It's going to give me a 0. So this one is going to be D. Leaving the last one for this sine function, right? So this, where was that sine function? There it is, B. Okay, so this one's B. All right. So that's that one. That's pretty exciting stuff. Now, let's see here. All right, so here we're doing a right Riemann sum. Okay, so basically, this is sort of one of the last things that we're going to do with this unit here. So when time is 0, my velocity is like 25. I'll write 25 up here. Okay, all right, 20. Then I'll write 15, 10, and 5. So I've got that one. Okay, then I got 20. At 1, my velocity is 20. Okay. At 2, my velocity is around like 16 here. So right around there. At 3, my velocity is like 12-ish, 12. And at 4, my velocity is about 10, right around there. Now, I'm doing a right Riemann sum, meaning that I'm going to break this into, let's see, 4 rectangles. It specifically says 4 rectangles. So I'm going to have 1 rectangle, 2, 3, and 4 rectangles. And since it's a right Riemann sum, I'm going to be using the right portion of the rectangle as its height. So there's 1 rectangle. There's the other, right? There's the other. And there is the other. That is the right, Riemann sum. And now I just have to add up all of these rectangles. So each one of them is 1, okay? So it's 1 unit long times, what is this going to be here? What is that? That was a 20. Oh, it was supposed to be like right there. 1 times 20 plus, I guess, 1 times 16. 1 times 16, right? Plus 1 times, what is this one? 12. And plus 1 times 10. Okay, notice this 1 is always the same. So we could actually factor that out, and it's actually just 20 plus 16 plus 12 plus 10. That's what you would really do. And by the way, how do you get this actual 1 here? This 1 is actually equal to the entire sort of range here, okay? So from 0 to 4, all right, divided by the number of rectangles. So 4 minus 0 divided by 4 rectangles. And you would end up getting this 1 here. That 1 is equal to 4 minus 0 over 4, where 4 is the number of rectangles. This is the sort of upper bound, and this is the lower bound as well. And there, I think that answer is on here somewhere. If I add that in my head, I'll probably mess it up. So 20, 30, 40, 58. We're getting to 58. There it is, 58. Okay. So there's that one. It was a Riemann sum. What do we got here? Midpoint, a midpoint Riemann sum. Okay. Now, let's see. This one's tricky. So we're going to have 3 intervals of width of 2. So this is actually kind of nice. They set it up for us. Here's one interval. Then here's another interval. And then here's another interval. And we're actually going to use the midpoints. So we're going to use the y value for each of these midpoints as our sort of top of our height. But each one of these intervals is 2 units large. So it's 2 times 0.25. Okay. We're going to do a midpoint. So I'm trying to find the midpoint of this interval, 0 to 1. And they're really nice because they give us everything we need here. Plus 2 times 0.68 plus 2 times, I guess, 0.95, okay? Where 2 is the width of each of the rectangles, so from 0 to 2, then from 2 to 4, then from 4 to 6. And these are the height of each of these rectangles, and they ask us to use the midpoint there, okay? So that's that one there. We'll leave that one like that. And I have a different question here. Did I do that one? Let's see. I think I did it. I did. Here, give me 1 second to kind of clear some of this stuff off. I think I got to paste it into the right location. Now, I've been asking us to look at some of these free response questions as well. So I've chosen another free response question. Okay. And I kind of want to show you guys how to do this one. All right. So let's put that one down here. Okay. So here's another free response, and it's a pretty nice one. Yeah, all in all, pretty fancy. It's got some fun stuff to it. So here it is. Consider the differential equation, the following differential equation. Okay. And there it is. It's dy over dx equals 2x minus y. All right. First question is A. Let me see if I can. A. It's not very thick. Go a bit thicker on those. There. That's better. It's still not that great. I'm going to go here. Whoa, that's way too thick. Sorry, guys. There we go. We'll do that one. All right, we'll leave it at that. Okay. So on the axis provided, sketch the slope field for the given differential equation at the 6 points indicated. So here they are, 6 points. 2, 1, -1 are my y coordinates. And I got 0 and 1 for my x coordinates. Okay. So I'm just going to make like a chart here, right? X and y. And it looks like I've got x coordinates of 0, 0, and 0. And I've got y coordinates, or x coordinates of 1, 1, and 1. And then they each have their corresponding y coordinates. So I've got one for 0, -1, right? So 0, -1, 0, 1, 0, 2, and then I've got 0, let's see, I've got 1, -1, 1, and 2 as well. All right. So that's what we're looking at there. Okay. Question is, how do I figure out the slope? Well, this is it. dy dx is the slope. So I just take these values, 0, I plug it into here, and then -1, I plug it into y, and I get my slope. So 0 minus a -1 is a 1. So I'm going to write dy dx is 1. Okay, like that. All right. Now, here, when x is 0, y is 1. So I'm getting a negative slope, -1 slope. When x is 0, y is 2. So I'm getting a -2 slope. So for all of these ones, for 0, -1, I got a slope of 1, which is something like that. For 0, 1, I got a slope of -1, which would be something like that. For 0, 2, I got a slope of -2, which would be something like that. So you want to just kind of make a general slope thing there. Now I do the same thing here. So 2 minus, so I'm getting a slope of 3 here, right? Because I just plug my 1 in for x, and I plug my -1 in for y. So there it is, getting a 3. Plug my 1 in for x and my 1 in for y. So 2 minus 1, what's 2 minus 1? Is going to be a 1. And then it's going to be, I plug my 1 in here and my 2 in for y. So 1, so 2 minus 2, oh, I'm getting a 0. Okay. So at 1, 2, so 1, 2, I've got a slope of 0. At 1, 1, I have a slope of 1. And let's see, what else do we have here? 1, -1, I got a slope of 3. So it's a pretty steep slope. There it is. That one's done. All right, that's part A. Okay. Let's go with part B. All right, shall we? I'm going to move down. I'll take this guy with me. Oh, I lost my slopes up there, but that's okay. Here we go. Find d2y over dx2. So this is basically, you're asking you to find the second derivative here, okay? So this is part B. Find the second derivative. Well, I know that dy dx is 2x minus y. So if I just apply another derivative to this, right? Another derivative to this side, then I'm basically finding my second derivative now. All right. Keep writing an x there, but it's supposed to be a y. There we go. So this is dy dx times dy dx. So that's just dy dx squared, written as this, or the second derivative here. This derivative distributes over this entire function. The derivative of 2x is 2. The derivative of y with respect to x is dy dx. How's that? That's pretty cool. And we got it. But wait, dy dx is 2x minus y. So my second derivative is 2 minus dy dx, or 2x minus y. All right. They also want us to do this, is determine the concavity of all the solution curves for the given differential equation in quadrant 2 here, okay? Now, basically they're asking you to find the concavity of all of the general solutions, or specific, all the general solutions, and they want us to focus on quadrant 2, okay, which would be this quadrant. Now, in that quadrant, x is less than 0 and y is greater than 0. So what I'm going to do is I'm going to look at this and I'm going to kind of stick these guys in here, and I'm going to say 2 minus 2, x is less than 0. So it's going to be some kind of negative number, right? Minus some kind of positive number, right? So 2, this is a negative 2, so that's going to end up being a positive. So it's actually just going to equal 2 plus some positive number, and then plus another positive number, right? So, because this negative distributes into here, making this, right? So my dy dx, which remember, my second derivative, this is my second derivative here, it always tells my concavity. So what's 2 plus a positive number plus another positive number? This is positive, or this is greater than 0, right? And so in justification, give the reason for your answer, we would probably have to write down something like that. In Q2, d2 dy dx2 is greater than 0 for all values of x and y. Okay, here's my justification. So therefore I would, the question is what's the concavity? I forgot to answer the actual question. So it's concave up. All right. Man, if I hadn't written concave up, I would have missed a point on the AP exam or something there. Okay. Oop. All right. So there's B. That one's done. Moving down. I'm going to do part C. Let y equal this function and be the particular solution to the differential equation. Let y equal f of x with the initial condition f of 2 equals 3. All right. So basically what they're telling us here for part C is that when y equals 2, x equals 3. I think that's what we've got, right? No, sorry, the other way around. When x equals 2, y equals 3. All right. So we got that. Question is, what do we want to do? Does f have a relative minimum or a relative maximum, or neither at x equals 2? Well, look at this. They give us x equals 2. How do I find maximums and minimums? I have to know if the derivative, or the dy dx, if it's equal to 0. That's my question, right? So, well, dy dx is 2x minus y, or 2x minus y. Well, they give us x. X is 2, and y is 3. There it is. So this is 4 minus 3, or 1. Aha. So dy dx is not equal to 0 at, I guess we could make our point, 2, 3. So therefore, it is neither a maximum, so no max or min at that point. Or you can even just write 2, 3. Pretty cool. So there's my justification. Remember, you got to justify, right? So my justification is that I've written here. So if I stop here and I just write no max, you might not get some points here. So neither. You just write neither. Some students would just maybe write neither right here, or neither, depending on how you want to say that. Because, but if you don't write any of this stuff down here, you're getting pretty skimpy on your justification. So you want to get your justification going there. All right, so there's that one. Let's do part D, shall we? Part D. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay. So they're actually giving us the answer here. They're telling us the answer is y equals mx plus b. That's pretty cool. That's the solution. Now, they want us to find the m and the b. So, you know, m's going to be something and b is going to be something. Whatever, like going to be a 4 and a -1. All right. So 4 equals -1. Now, if I have this equation, y equals 4x minus 1, and that needs to be the solution to this differential equation. Okay. So question is, how do I solve this guy? Well, they're giving me this. So I'm going to take the derivative of this and I'm going to write it down. So dy dx is simply just, I guess, m. All right. Well, that's funny. All right. So dy dx is actually just m. Okay. But dy dx is actually also equal to 2x minus y. That's right. dy dx is 2x minus y. Okay. So this is what I'm looking at. But wait, y is also mx plus b. Ah, interesting. So I'm going to be able to write this. So m equals 2x minus mx plus b. All right. I guess I don't want this to equal sign there. Basically, what I'm doing is I'm saying, hey, I just took that y and I got rid of that. There it is. Okay. Ooh. Got my parenthesis. I'm going to distribute my negative sign. I'm going to get m equals 2x minus mx plus b. Okay. And now you're thinking, oh man, I got a lot of stuff going on here. So what are we going to do? What are we going to do? What we want to do here is we want to basically say, look, I'm trying to build a solution that works for all x and all y values. Okay. So basically, if I got something that works for all x and all y values, the x shouldn't matter. So I want to somehow remove this x. I want to remove this x here. How are we going to do that? I'm going to write it like this. I'm going to factor out my x, and I'm going to get x times 2 minus m plus b. Okay. Now, this is the logic here. In order for this to work for all x values, the coefficient in front of this x must be 0. Because if that's the case, then this x would get canceled. And therefore, what that would mean is this m and this b is going to function regardless of the value of x, because this is the solution for the whole thing. So all x coordinates. So how do I make this x go away? The only way that this x could go away is if m happens to be 2. Okay. So therefore, m must be equal to 2. I guess I'll write that out. Right? In order for the solution to be valid for all values of x. to be valid for, all values of x. That's my justification here. Because now, if I make m equals 2, so I'm going to let m equal 2. So I'm going to write that 2 equals x times 2 minus 2 plus b. Okay. Oh, sorry guys. I'm sure some of you guys at home caught that. It's supposed to be a negative here because this negative distributes into the b. See that? Okay. So now look at this. So then I get 2 equals, doesn't matter what x is, x times 0 minus b. Well, what's x times 0? Well, it doesn't matter. So that what this means is that x could be anything. Could be 10, it could be 5, it could be million, it could be a zillion. If m is 2, then we're good to go. Okay? So that's what that basically means. And so basically 2 equals negative b, which basically means b equals negative 2. So if we let m equal 2, b equals negative 2. Oops. And in the end, we get it. This is the m and the b that works for this differential equation. And the tricky part is knowing that in order for your solution to work, you want it to work for all values of x. Okay. And let's say you had done something different and you'd end up having a y somewhere in here. You'd have to go through the same reasoning. You'd have to set m or b equal to something such that the y has a coefficient of 0. All right. And that's what you would end up having there. All right. All right. Well, that was pretty fun. Hope you guys liked that one. It was a long one. And yeah, but I think I'll sign off for the evening. Enjoy the rest of your night.